Since the average is the sum of the data values divided by the number, it is a sum of scalar multiples of a random variable. So if the random variables are normally distributed, we can find the distribution of the average if we want to. For example, suppose we have 3 random variables representing the values of 3 different investments, and each is normally distributed with the same mean and a different variance. Let phi denote the cumulative distribution function of the standard normal variable, and let's determine the probability that the average value exceeds 106. So the average value will be the sum times 1/3, which is a sum and scalar multiple of normally distributed random variables. So the mean will be the 1/3 of the sum of the means, and the variance, well, a constant multiplier comes out as a square, and the variance is sum, and so we know the variance of the first, second, and third. And so our standard deviation will be the square root of the variance. So the average value will have mean and standard deviation, and we want the probability that the average is greater than 106, and so our z-score will be but the probability that z is greater than 2 is complementary to the probability that it's less than or equal to 2, and so this probability will be, and in terms of our cumulative normal distribution function, that'll just be phi of 2. So an important idea is to solve it again. So the average value of the 3 investments is 1/3 of their sum, but if the average exceeds 106, then the total value must exceed 3 times that amount. So let's use the total value of the investments instead. So the mean will be the sum of the means. The variance will be the sum of the variances. And our standard deviation will be our z-score will be, and that's the same z-score as before, and so nothing else changes. So this is commonly used when we're measuring things. We take a series of measurements and find the average. So let's do that. If E1 and E2 are the 2 errors, the average error will be half the sum. And again, this will be the sum and scalar multiple of 2 normally distributed random variables. And so the mean will be the sum of the means. The variance will be that factor 1/2 comes out as a square times the sum of the variances, which will be, and so our standard deviation is, and so the error will be normally distributed with mean and standard deviation. Now, note that our standard deviation is given in terms of h, and that could be a problem, but let's not borrow trouble. For the average to be within 0.005 h of the actual height, we need the error to be within the interval. And our z-scores will be, and likewise for the negative value. And so the probability we're in the interval is the probability that we're to the left of 1.4 minus the probability we're to the left of negative 1.4. And again, by symmetry, the probability that we're less than a negative is the same as the probability we're greater than the positive. And this probability that we're greater than 1.4 is complementary to the probability we're less, and so we can look up those values on the table to find our probabilities.